Hey there, pre-calc friends. Shinners is here, ready to walk you through 9.2 summation notation. Before we jump in today, make sure you either have a physical TI-84 or you are using the TI-84 app. The link we did send out, it works for Chromebooks. Or I believe decimals will also work. What won't work is if you have a TI-83 or lower, it just doesn't have the nice summation notation that we're going to be using today. All right, so grab one of those and let's get started here. Before we jump in, I want to just review what the heck we did last week. We talked about sequences, and a sequence is some sort of ordered or patterned list of numbers. And we talked about how you can have an arithmetic or geometric or a sequence that might not fit either category, and we might categorize it as other or neither. And so what we're going to be doing today here is, hey, let me just give you this random sequence. We'll make it arithmetic with adding 1 each time. Very easy sequence. And so what we're going to be doing today here is we're just going to be adding up all the terms in my sequence. And there's a lot of real world applications that we'll get into later this week. You can think of a sequence might be, I know I put money away in my retirement fund every month. So lots of things like that, like loans, a lot of that can be modeled using a sequence. And sometimes it might make sense to add up all the terms in our sequence. And that's what we're going to be doing today. So in order to do that, we're going to be using this funky dunk thing called summation notation. Nice little rhyme for you there. You might also hear it sigma notation. This symbol here is called a sigma. It's a Greek letter. And what summation notation is going to do for us is it's just a concise way to express a sum. So we're going to be adding up all of the terms in a sequence, and depending how long your sequence is, it can get very cumbersome to write that all out. So it's just basically think of it as a shortcut. And so how summation notation works is there's really 3 places that you have to pay attention to. The first is this spot to the right of the sigma. And in that spot, you'll see the explicit equation for your sequence. So if you remember from last week, we talked about how explicit equations are nice because you can plug in any term index, any term number, and the output will be that term. So this is a quick way to get the 100th term in the sequence without necessarily needing to find the 99th term, which is how recursive works. So that's that spot. This spot down here is basically your start. It is the first value you plug in into your explicit equation, okay? And so if down there is the start, maybe you're going to guess that that's your end. That's going to be the last value you plug in. So maybe you're going to add up 100 terms. Maybe you're going to add up 200. In fact, we can even add up an infinite sequence, which is called a series, an infinite series, where we add up an infinite amount of numbers. And not to totally blow your mind, but we might get into that a little bit, which is exciting. So if you see an n up there, that just means the sequence is never ending. It's infinite. So you're not going to plug in a number and end. It's going to approach infinity, which is kind of cool. Okay. But not to confuse you just yet. Let's see this in action here, folks. So in example 1, I'm just writing out each sum. So I don't need to actually find the sum. I'm just writing it out. So this might actually show us why we need summation notation because it can get a little bit annoying to always write it out. So let's take a look here. To the right of my sigma, that is my explicit equation. Down below, it tells me where I'm starting. So I'm starting with plugging in 1 for k, and I'm ending with plugging in 6 for k. So I'm going to plug in all of the whole numbers in between those two endpoints. And the last number I plug in is 1/6. All right. Letter B, this is my explicit equation. And I'm not sure if you've seen that before. It's not just a K that's very excited. K, yes. It's not that. That is called a factorial. I don't know if you've seen these before. If not, it's called a factorial. And for example, if I wanted to find 6 factorial, I just take 6 and I multiply it with all of the whole numbers that come below it. And then 1 is the last number. So that's just a little example here, but it looks like I'm starting with 1 factorial, and then I'm plugging in 2, and then 3, and then 4. And just to kind of help you with the factorial aspect of it, just so you know, this is how each of these factorials would look like. So you just multiply all of the numbers below it and end with 1. And with both A and B, I hope you guys can see that in both of those, I could type in those expressions into my calculator and I would get a number answer, right? An actual solution here. However, in letter C, this one looks a little bit different, right? So I have the same explicit equation. It's a factorial again. And it looks like I'm plugging in 1, but when I look at my end, it's an n. So that's an indication that this sequence is going to go on forever and ever. So it's going to approach infinity. I'm never going to have a last number that I plug in, right? Because the biggest number you can think of, you can always add 1 to it. So this would be what I might call an infinite sequence or an infinite series, which just means it doesn't have an end. So if you see a variable up here, that's an indication that it goes on forever and ever to infinity and beyond, to quote Buzz Lightyear. And so for this case, I couldn't really plug that into my calculator, right? And get an actual numbered response, like a number answer. So that one's a little funky, but kind of cool to think about. I love thinking about infinity. It can really blow your mind. In example 2, we're just going to do it the opposite now. So I'm giving you the values of a sequence being added together, and you give me the sigma notation that goes along with it. So there's my sigma. I'm going to find the explicit equation and put that to the right of sigma. So looking at the terms in my sequence, what am I doing each time? I'm taking whatever the index is, and I'm squaring it, right? So I'm just doing k squared. I'm starting with 1, and I'm ending with 5. So you can start to see how this sigma notation is really a nice shortcut for us. This example is a little trickier because you can see this is an example of an infinite sequence. It doesn't have an end. So my equation is just going to be that, with n being the last thing I plug in, but n is approaching infinity. So it's going to keep on, keeping on. And so I just really have to figure out, what is my start? So what number did I start with? So it looks like my term is 1, but what would I plug in to the equation in order to get a 1 there? So usually our sequence starts with an index of 1. So you might just try plugging in 1, and let's see what happens. This is supposed to be an arrow. So I get 1 minus 1 in my exponent, which is 0. And anything to the 0 power is 1. So I get 1 divided by 1, which is 1. So just as we expected, K does equal 1 in this case. That's my start. But remember, you don't always have to start with 1. So if that didn't work out, we might have to play around a little bit further in order to get the correct start. So you can actually see that down here on letter D, we're starting with 4. Okay, so don't always necessarily have to start with 1. So keep that in mind. So that's kind of how sigma notation works, but now let's actually use it to find a sum, right? Sum means add it all up, get a total. And so let's actually do that here. So with letter A here, we are going to have to plug in 1 for K, and then I'd have to plug in 2, and then I'd have to plug in 3, all the way up until 26. And I'd have to add up all of these values. So that would be kind of a lot of annoying work. And so this is where it's really important that you have a TI-84 or you have Desmos open, because we're going to want to use the summation notation calculator aspect, okay? So let me show you what that looks like. I'll do some on the TI-84, and then I'll do one on Desmos just to show you. But you're going to want to be in sequence mode. So press mode and then go down here, and you're going to click the SEQ button, sequence, which is our last mode of the year. We covered all of them, so that's kind of exciting. Mr. Gibbon and I joke that pre-calc should be named, this is the class where you figure out all the other modes on your calculator, right? Because that's really what we do. Press math then, and then scroll up so you can get to this summation, and then you see that sigma right there. It looks like a 0, or maybe the letter O, whatever you want to think of it as. I think it's a 0. And we are going to plug in this this problem here. So click on the variable button, and it's going to be n. So it's just that xt theta n button. Now it's going to be an n for sequences. Our book more so uses Ks versus our calculator and Desmos uses Ns. But just like anything in math, folks, the variable can be very interchangeable. It's just what the variable represents. So as long as you're consistent using either variable, you're good to go here. So I plugged that in, and I get a grand total of 871. And it took me way less time than had I plugged it in all by hand. So that's kind of cool here. Alrighty, let's try this next one. I'll use Desmos for this just to show you what that looks like. So you're going to want to click on functions and then go to miscellaneous. You're going to click on the summation, the sigma there. For letter B, we're starting at 1, and we're going up to the 12th term. You're going to want to use parentheses here, otherwise Desmos gets confused. And we do want to be consistent with our variable. So if we're using n, let's keep using n. N squared minus 4 in parentheses gives me 602. So letter B gives me 602. Letter C is a little funky because if you look, there's no input, there's no K, there's no N. So I'm really just adding 6 50 times. So you can actually just do 50 times 6, which is 300. But if your brain didn't go there for whatever reason, you can also just do, oops, not 0, 1, 250, and then do 6 for the explicit equation, and you get 300 as well. Alrighty. Let's try letter D here. So this is the one I told you to watch for, because as you can see, I'm not starting at 1, I'm starting at 4. So n equals 4 to 24. So maybe for whatever reason, I want to count up the 4th to the 24th months of rent I've paid or something, right? So you don't always want to start at 1, maybe. And then we're cubing that. So I imagine a fairly large number. There it is. 89,964 is the sum for that one. And now for letter E and F, hopefully these look a little familiar to you. These are the ones that we did up here. So it just goes to show you that you can always write it all out and do it that way if you like. But I do think the summation